Welcome to the 9th lecture of module 5, which we are discussing on distillation. In our previous lecture, we have considered how to handle the subcooled reflux, and second thing we have considered use of open steam. In this lecture, we will primarily focus on how to handle the multiple feeds. And second thing, if there is a side stream withdrawal, we will first consider multiple feeds problem and then we will come to the side stream withdrawal problem. Let us consider multiple feed problems and we can solve it similarly like McCabe-Thiele methods. So, this is a distillation column where two feeds are introduced at two different trays. Feed 1 and feed 2 should have the different compositions, and then two feeds we can handle in the same fractionator. Let us see how to handle this problem. So, we will do the material balance for each components and the mass balance. There are primarily three sections. Section 1 above the feed tray, and then the second section which includes the feed 1 and then stripping section. Section 1 which represents the enriching section, section 2 which is taken into account the feed 1, and section 3 is for the stripping section. Let us do the material balance for section 1. If we considered a small envelope considering the reflux drum and distillate and the reflux, the material balance over this we can write G is equal to, if this is L, then would be L plus D, and if we define the reflux ratio which is R is equal to L by D. So, that we can write G is equal to R D plus D is equal to R plus 1 into D. Therefore, we can write G by D would be equal to R plus 1. Now, if we do the material balance for particular components, if we consider envelope 1, then we can write G y n plus 1 would be equal to L x n plus D x d, and from this we can write y n plus 1 would be equal to L by G x n plus D by G x d is equal to R by R plus 1 x n plus x d by R plus 1. This is already we have discussed. This is the equations of the operating line in the enriching section or rectifying section, where the slope of the operating line is R by R plus 1 and intercept is x d by R plus 1. If we consider envelope 2, it incorporates the feed 1. then we can calculate L dash and G dash from the vapor and liquid compositions, which is from the flow rates of the liquids and gas in each tray. Now, if we do the overall material balance, it would be F ZF plus G dash Y dash would be equal to X L dash plus D X D. So, we can write Y dash would be equal to L dash by G dash into X plus D X D minus F Z F divided by G dash. This is the operating line for the intermediate section. Operating line equations for the intermediate section. So, now we will consider the stripping section as we did earlier. If we do the material balance, it would be Lm bar x m is equal to G m bar y m plus 1 plus W x w, and if we put G m bar is equal to G bar is equal to L m bar minus W is equal to L bar minus W, then Y m plus 1 would be equal to L bar by G x m minus W by G bar x w. So, this is the equation of the operating line we have discussed earlier in the stripping section. Operating line, and this is for section 3. For a given reflux ratio, we can plot the operating line, the rectifying section, and then this is for stripping section and this is for intermediate section. Now, this intermediate section operating line coincides at two different feed plate locations, and that will be decided from the feed line. Suppose this is the feed plate and we know the feed flow rate and compositions, and then we can write the slope of the Q line, which we have discussed earlier. This is the slope of Q line, and which based on that we can say where the feed line will intersect. Consider two feeds, feed 1 which is a saturated liquid of composition ZF1 and feed 2 is a saturated vapor of composition ZF2. So, for saturated vapor at a particular feed, the Q line slope would be 0, and for the saturated liquid Q would be 1. If we can draw the operating line for the rectifying section, this is the ZF1 which is as composition ZF1, and with a saturated liquid if we plot with a slope of 1, then it will intersect the stripping section line and the starting point of the operating line in the intermediate section. Similarly, it would intersect the other feed points between stripping section and slope of the Q line of the other feed, feed 2 ZF2, which is a saturated vapor which intersects over here. Let us take an example. Two feeds were fed in a distillation column. Feed 1 which has a 100 kilomole per hour saturated liquid with 60 mole percent n-hexane and 40 mole percent n-heptane, and feed 2 which is 150 kilomole per hour saturated vapor with 50 mole percent n-hexane and 50 mole percent n-heptane. The top products contain 96% n-hexane and residue contains 4% n-hexane. The reflux is a saturated liquid and the reflux ratio of 1.5 is used. The relative volatility of n-hexane in the mixture is 2.36. Find out the number of ideal trays required for the given separation and identify the locations of feed trays. Let us take a basis of 1 hour operation. So, F1 is given 100 kmol per hour and F2 is given which is 150 kmol per hour. If we do the total material balance, then F1 plus F2 would be D plus W, which we can write 100 plus 150 would be equal to D plus W. We can write D plus W would be equal to 250. Suppose this is equation 1. Now, if we do the balance on the n-hexane, we can write F Z F1 plus F1 and F2 Z F2 would be equal to D x D plus W x W. We can write 100 into 0.6 plus 150 into 0.5 would be equal to D into 0.96 plus W into 0.04. This would be equal to 0.96 D plus 0.04 W would be equal to 135. Say this is equation 2, and if we substitute from equation 1, then we can write W is equal to 250 minus D, and if we substitute in equation 1, D would be equal to 135.9, and if we substitute this in equation 1, W would be 250 minus 135.9, which would be equal to 114.1. So, the distillate and the bottom flow rate we could able to calculate with the total material balance. Let us consider the rectifying section 1 over here. So, the reflux is a saturated liquid. So, we can write R is equal to L naught by D, and therefore, we can write L naught would be R into D, which would be equal to 1.5 into 135.9, which is equal to 203.9, and G1 gas flow rate would be R plus 1 into D, which is 2.5 into 135.9, which is equal to 339.8. So, the equations of the operating line as we have derived earlier, y n plus 1 would be R by R plus 1 x n plus x d by R plus 1. So, this would be equal to 1.5 divided by 1.5 plus 1 xn plus x d is 0.96 divided by 1.5 plus 1. So, we could write 0.6 xn plus 0.384. So, this is the equations of the operating line in the stripping section. We know the equilibrium relations which is given, use the relative volatility equations and we can calculate the equilibrium data. So, x and y value can be calculated like this and we can plot the equilibrium line. And we locate the feed points over here, that is ZF1 which is 60% and 50% is for ZF2, XW is given which is at 0.04 which is over here, and then the equilibrium data are plotted over here which is shown in the blue line, the equilibrium curve. As we have calculated, intercept is x d by r plus 1 which is 0.384. So, from this intercept and with the x d and x d which is 96% is given over here, we can plot the operating line. So, this is the operating line for the rectifying section. For rectifying section. Now, for section 2, the liquid rate which is equal to L dash would be equal to L naught plus F 1. Since the feed 1 is a saturated liquid, the feed flow rate in section 2 would be enhanced by F 1. So, the total flow rate would be 203.9 plus 100 which is equal to 303.9, and gas rate which would be remains same, G dash would be G 1, that is in section 1 which is 339.8. So, the operating line equations, y dash would be equal to L dash by G dash x plus d x d minus f z f by G dash. So, if we substitute, it would be 303.9 divided by 339.8 x plus 135.9 into 0.96 minus 100 into 0.6 divided by 339.8. So, which would be equal to 0.894 x plus 0.21. So, this is the operating line equations for the intermediate section. Now, let us consider section 3, that is the stripping section. Where the liquid rate remains same, which is L dash, because the feed 2 is a saturated vapor and G bar would be equal to 339.8 minus F 2, which is equal to 339.8 minus 150, which is around 189.8. So, we can write y m plus 1 would be L bar by G x m minus W by G bar into x w, which is equal to 303.9 divided by 189.8 x m minus 114.1 divided by 189.8 into 0.04. So, which would be 1.6 x m minus 0.024. So, this is the operating line equations in the stripping section. With this, we can now plot the equilibrium. We know how to plot the equilibrium line, and we know the intercept for the intermediate operating line. So, this is the intersection, and the fit is a saturated liquid which intersects over here. So, from this point we can draw the operating line of the intermediate section, and we know the fit conditions over here at Z f 2, and it is a saturated vapor. The Q line equations is this. So, these are the Q line, this is Q line, and this is Q line for fit 2. It intercept over here. We can now join the operating line equations for the stripping section. Now, we can do the staircase construction to obtain the number of ideal plate requires, and the shifting occurs at the intersections point from the intermediate operating line to the stripping section, as well as intermediate operating line and rectifying section operating line. We can see number of ideal stages required is equal to 16, and the first crossover occurs at plate number 5, fifth tray for feed 1, and ninth tray for feed 2. So, this is the feed plate locations. Let us consider another important thing, which is the side stream. We have a single feed column, and we have intermediate product withdrawal. So, at a certain plates there is a side streams withdrawal. We can use the multiple mass balance envelope as we did before. First envelope we will consider without considering the side stream. So, we will get the operating line for the rectifying section. So, this is the operating line for the rectifying section. Now, if we include the side stream and do the material balance for the key component, we can write G n plus 1 y n plus 1 would be equal to L n x n plus L s x s plus d x d. So, this is the material balance equation, and if we rearrange, it would be y n plus 1 would be L n by G n plus 1 x n plus L s x s plus d x d divided by G n plus 1. So, L s is the rate of side stream which is withdrawal, and its composition is x s. This would be x s and x d. This is the equations of the operating line considering the side stream, and it would intersect both the operating line of the enriching section and the operating line considering the side stream will intersect at a point x is equal to x s. Now, if we do the material balance for the stripping section, L bar x m would be G bar y m plus 1 plus w x w, and if we rearrange this, we could write putting G bar would be L bar minus w. So, therefore, we can write y m plus 1 would be L bar by G bar x m minus w by G bar x w, which is equal to L bar minus W x m minus W by L bar minus W x W. So, this is the operating line equations for the stripping section, and we can plot the operating line. This is the operating line for the stripping section, and this is the operating line for the intermediate section, where it intersects at x is equal to x x at these locations, and then this is the fit conditions Z f, and it intersects at this location since it is a saturated fit. For the determination of the minimum reflux ratio for this type of column is bit tricky, because the pinch point may occur at the intersection of the feed line or the side line and the equilibrium line. If the equilibrium curve has any unusual curvature, a pinch point may be found out by drawing an operating line that touches the equilibrium curve. Now, let us take an example of this type of problem of side stream withdrawal. Equimolar compositions of N-hexane and N-heptane is subjected to a fractional distillation at 1 atmosphere pressure and with a feed flow rate of 100 kilomole per hour. A liquid side stream of 70 mole percent N-hexane is to be withdrawn at a rate of 20 kilomole per hour. The top product contains 90% N-hexane and the residue contains 5% N-hexane. The feed is saturated liquid. The reflux is a saturated liquid and reflux ratio of 2.5 is used. The relative volatility of N-hexane in the mixture is 2.36. So, find out the number of ideal trays required for the given separation and identify the tray from which the side stream should be withdrawn. Let us consider this is the column where we have 3 sections, one without side stream and another without considering side stream, the other one is stripping section. We can write basis 1 hour operations and feed is given 100 k mole per hour and reflux ratio is 2.5 is given. Then the equilibrium data is given. We can plot the equilibrium data. Overall material balance if we do, then we will have F would be equal to D plot side stream, we can write Ls plus W. This we can write 100 would be equal to D plus 20 plus W. So, this would be D plus W is equal to 80. Now, if you do the material balance, F Z F would be equal to D x D plus L S x S plus W x W. 100 into 0.5 would be equal to D into 0.9 plus 20 into 0.7 plus W into 0.05. So, from this we can calculate 0.9 D plus 0.05 W would be 36, and substituting the values from this D plus W is equal to 80 in this equation, we can calculate D is equal to 35.56 and W would be equal to 44.44. Now, let us consider the rectifying section. Rectifying section above side stream. above side stream, R is equal to L naught by D. So, L naught would be R into D. So, which is equal to 2.5 into 35.56 and which would be 88.9, and G 1 would be R plus 1 into D and which is equal to 124.46. Now, the equations of the operating line y n plus 1 would be R by R plus 1 x n plus x d by R plus 1, which is equal to 0.714 x n plus 0.257. So, this is the equations of the operating line in the rectifying section. Now, section 2 including side stream, we have operating line equations. Y dash would be L dash by G dash into x n plus L s x s plus d x d by G dash. So, we can write L dash would be L naught minus L s, because the side stream is withdrawn. So, the flow rate in this section would be reduced by L s. So, it would be equal to 88.9 minus 20, which is equal to 68.9. Now, the gas flow rate G dash would be similar to the rectifying section, which is equal to 124.46, and so the operating line equations would be y is equal to 68.9 divided by 124.46 x n plus 20 into 0.7 plus 35.56 into 0.9 divided by 124.46. So, which would be equal to 0.554 x n plus 0.37. So, this is the equations of the operating line for the intermediate sections. For section 3, that is stripping section, the liquid flow rate L bar would be L dash plus F, which is equal to 68.9 plus 100, which is 168.9, and gas rate is G bar would be G dash, which is equal to 124.46. So, the equations of the operating line for the stripping section, similar way we can write y m plus 1 would be equal to, it is coming out to be 1.357 x m minus 0.018. So, we know the equilibrium data, since the relative volatility of the system is given from the earlier examples. We can use this equilibrium data, we can plot the equilibrium line, and side stream which is given at a intersection points 0.37, this is over here. So, it is for the side stream and which will intersect at a point over here. So, this is the point where x would be x s, and at this point the slope of the intermediate section line is given and the intercept is 0.37. So, we could plot this equations, and then we know the fit conditions, which is 50% equimolar, and we plot the Q line. This is the Q line, and we have the operating line for the stripping section, which intercept the Q line at these locations. Then we can just make the staircase, and we should shift from the intermediate section operating line to the stripping section operating line at the fit plate. This is the locations where the shift from the intermediate section operating line to the stripping section operating line occurs. Total number of ideal trays is equal to 8, and the locations of the fit tray is 4. Location of fit tray is fourth plate. So, thank you.